Okay, so it's time to start. It is a great pleasure for me to introduce Ali Yazdani again. For those of you who are not present yesterday, I'm going to repeat some of the introduction, but a shorter version. He's going to tell us today, he's going to deliver his second Loeb lecture. Ali did seminal work in the study of strongly correlated electron physics, mainly using scanning tunneling microscopy, and he's going to tell us a little bit about the technique and some of the really recent results. In fact, told me that this image was just collected yesterday, so things are happening as we speak. Ali did his undergraduate at UC Berkeley, then graduate work at Stanford, working with Aaron Kapitulnik on the study of the superconductor insulator transition. He then joined IBM Almaden and worked with Don Eigler to study scanning tunneling microscopy and spectroscopy, including moving individual atoms on very clean surfaces. And there he studied some properties of magnetic impurities on superconductors. He then joined the physics department at the University of Illinois at Urbana. Spent there, I believe, something like 7 years, and in 2005 joined the Princeton faculty, where he is there until now. He has been awarded a tremendous number of recognition for his work. I encourage you to look at his CV. I'm not going to repeat it because it's just a very long list. And it's a pleasure to welcome Ali to give his second talk.
Thank you. Boy, people are even more formal at Harvard. Well, thank you for coming to listen to this second lecture. As Amir said, I'm going to talk about some very recent experiments. Is this mic working? Okay, great. And this second set of experiments that I want to tell you about today is where we try to use the scanning tunneling microscope to look for a very unusual quantum liquid, which has been proposed in correlated electron system for quite some time. So let me first tell you who's done all the work. And actually, some of these people got their start here in Cambridge. Ben Feldman was a graduate student with Amir. And he's led this project together with Malika Randeria. And she came from MIT, joined my group. And Andras Guinness was a graduate student with my group, which has also participated in these experiments. And what I'm about to tell you would have not been possible without collaborating with Bob Kava, who is one of our prize material growers in the country. We're very fortunate to have him. And collaborating with Alan MacDonald, providing quite a bit of theory support with his graduate student, Fencheng Wu. So let me start out by just reminding you where the word nematic comes from. Many of you are here, especially at Harvard, are familiar with liquid crystal phases, and which is a very useful thing where we use it to pretty much display many things these days electronically, as we all stare into all of these little devices all day long. And these nematic phases are rather beautiful to actually image and rather easy to image using basically polarization dependence of the scattering of light from them. And this is an example of a liquid crystal sample in which is undergoing a phase transition between a phase which I call nematic, which is, as you can see here, has some orientational order parameter, and a smectic phase that images differently under this polarizing microscope. And the black stuff actually is the liquid that's isotropic in the middle. So we've been looking for the quantum analog of these phases inside materials for quite some time. And the motivation for much of this comes from some early work that was done by Steve Kivelson, Eduardo Fratkin, and Vic Emery, in which basically they considered, motivated by many experiments in high-temperature superconductivity, where you could have electronic phases that basically broke this rotational symmetry, the symmetry of the underlying crystalline lattice. So we are looking at electrons which are living on a crystal. And we're looking for basically electronic phases where the symmetry of what we have in the resulting phase is basically being reduced from that of the underlying crystal. And we are looking for phases that form into these exotic type of liquids because of the interaction between the electrons. So you can obviously imagine, and I'm going to talk about this a little bit, you can put strain or all kinds of things inside the crystal which will prefer one direction over the other. But what we are really looking for are ways in which we're not just sort of trivially changing the behavior of electrons from one direction to another. We're really looking for ways in which interaction between the electrons spontaneously picks a particular direction, just like you would have, for example, in a ferromagnet. So the search for these things was motivated by finding what's called stripe phases in high-temperature superconductors, which I'll show you some examples of. And the fact that in Mott insulators, you have competing interactions, which our colleagues who do simulations tell us make these type of phases quite likely to occur. So at any point during this talk, please stop and ask questions if anything is unclear. This is more of a technical talk compared to yesterday. Thank you. So in this slide, the question is, what are the lines supposed to represent? This is sort of an artist's kind of rendition of, if you like, rivers of electron charge flowing through your sample. Okay? So in one case, the rivers are kind of frozen. You have a crystal. And in another phase, you can have, for example, stripe-like phases where electrons will preferably flow in one direction more efficiently than in the other direction. And in the isotropic case, it will flow in all directions. And we're looking for these phases spontaneously because of the interaction between the electrons. So looking for these kind of broken symmetry phases have been something that people using scanning tunneling microscopy have been doing for quite some time. My group has been working on it. Seamus Davis's group, Jenny Hoffman's group here at Harvard has been working on it. And in these high-TC superconductors, we know we have strong electronic interactions. And there are many experiments, and I don't want to get into the details, that show evidence of at least frozen sort of charge density wave-like phases. Okay? There is quite a lot of work that there might be some pneumaticity in these materials as well. But that is perhaps less agreed upon at the moment. Perhaps the material system, which is also a superconductor and also strongly correlated, which shows a stronger evidence for presence of these kind of pneumatic phases, which is the subject of this talk today, are iron-based superconductors. So these were discovered in 2008. And these are systems in which you have iron arsenide with various different components. And as you tune the composition of this material, you can have, again, antiferromagnetism, just like in high TC, and then you can have superconductivity at relatively high temperatures. And through a series of experiments, people have found that in these materials, when you measure the resistivity of the material in different orientation in the AB plane, these are also layered compounds. If you measure the resistance in plane along the A or the B direction of the crystal, the resistance as a function of temperature show basically an anisotropy that basically shows up as you lower the temperature. Now, the material do undergo a structural phase transition between a tetragonal to the orthorhombic phase, but there seems to be a lot of evidence that these type of anisotropies actually turn on at temperatures higher than the structural phase transition that happens in the material. This actually becomes somewhat of a key question to the exercise that I'm going to go through of what are sort of things you want to do in a model system. Here's an example of an STM experiment done by Abhay Pasupathy and his group, and there are similar results from Seamus Davis's group at Cornell, which find evidence that in these materials you can have domains, if you like, in which the electronic structure image in these STM experiments show different orientations.
So that's going on
So this one we don't know. The question was whether this is just a surface-sensitive experiment. But these are bulk-sensitive experiments. And we are very much convinced that these bulk-sensitive experiments, and there's also some optics experiments done that seems to suggest that this is a real phenomenon, this anisotropy.
And there's no strain? Is there a strain that somehow favors, gets them aligned in one direction as opposed to the other, as opposed to having domain?
So the question is repeated, what is the role of strain in the formation of this phase, and whether the strain can be used to align these phases. And the answer to the question is that you can use strain to align things. And in fact, this is kind of the question that has bothered me all along about these proposals, is how do you know whether underlyingly there is strain that stabilizes some anisotropy in the system versus truly the interaction between the electrons. So David is kind of stealing my punchline here. But let me just go and just show a few more things. So there is evidence in these iron-based superconductors that you might have a pneumatic phase which is anisotropic. You have fluctuations, which shows up in the resistance, for example. And the way you understand these things is that, for example, you have a Fermi surface on this compound, and somehow, whether it's a chicken and egg problem, whether you have interaction driving this instability, or you have some sort of a strain that turns on because of an onset of a structural phase transition, and how do you separate these two is quite a difficult problem. Now, let me also mention, since I put up this slide of fluctuations, the other reason we are interested in understanding these pneumatic things and their fluctuations is that there is quite a bit of theory that suggests that perhaps the fluctuations of these pneumatic orders can be useful in some theoretical models for creating superconductivity itself. Okay? So it could be an enemy of superconductivity, just like charge density waves often are enemies of superconductivity, or it could be a friend. We don't quite know. So lastly, and this is getting closer to the topic of this talk, we also have evidence in other interacting systems, like in particular two-dimensional electron gas in high magnetic fields, which show basically Landau physics and fractional quantum Hall physics. And in these experiments from Jim Eisenstein and others, Mansour Shahegan also at my institution, they see that as they cool down these samples, for example, in certain quantum Hall phases, so these are basically resistance showing the different quantum Hall phases that you can have with different fractions, you can have an isotropy in the resistance of the sample which can form as you form this quantum Hall phase. Now, there must be something in the sample that picks a direction, but the thinking is that you have a situation in which you have electrons strongly interacting with one another, and somehow this is driving the problem to pick a direction and becoming this pneumatic phase. Now, so we have a few problems. One of them is that strain is playing a role, undoubtedly. What you do to the sample to create an anisotropy is going to do something. And so in some sense, even theoretically, you do not expect to have a true long-range order of these pneumatic phases. You would expect to make domains in the sample. So there would be domains that you may be able to align using strain. But without that, you would expect that if spontaneously the sample picks a direction, part of the sample would pick one direction or another, you have domain walls. So this is where you might talk about some concept of vestigial order. You have something that is there, and you can kind of sort of align it a little bit if you provide some external perturbation. So in a sense, what this problem is looking for is a model experimental system. A model experimental system that can help us basically separate out things like the effect of strain, so what I call single particle effects, things having nothing to do with the interaction between the electrons. And where you can look locally, so this is where we come in, doing STM. And of course, what we would like to do is be able to demonstrate that the interactions that leave some signature on something we can measure about the property of the system is actually the thing that's driving the anisotropy in the experiment. So this brings me to the experimental system we're going to talk about. We're going to talk about electrons in a 2D electron gas at high magnetic fields, where we have the quantum Hall physics in the simplest case. Okay? And this problem actually was considered that these quantum Hall systems can provide such a model system, provided that the quantum Hall took place in a system that had basically valley degeneracy. So the Fermi surface of a quantum Hall system, if it has different kinds of valleys, in this paper, Abinan, Sondi, and Kivelson basically proposed the idea that because of interactions, you can spontaneously have the system pick some subset of these underlying valleys and drive the system into a nematic phase. So this is a purely electronic driven proposal. You have Coulomb interaction basically driving the system to pick. Well, they picked one or two, or you can have a combination of one and a combination of two. This can go in a number of different ways. Okay? So what's nice about this is that if you think about interaction in these systems, if you could measure basically the spectroscopic property of the system, so without interaction, you'll just expect to get a bunch of Landau levels at high magnetic fields, electrons basically being degenerate inside these Landau levels. And now, if you turn on the interaction, and the interaction is strong enough, you can induce, like an exchange-induced gap into these quantum Hall Landau levels. And they basically proposed, this is actually from their picture, that if you could somehow, they didn't say this so much in words, but they just did it in a picture, if you could actually image the cyclotron orbits of the electrons, you could actually see this anisotropy basically form. Okay? So it's the ability to be able to connect these two experiments gives us a chance to perhaps provide a model system that you can actually look at the wave function and also measure the spectroscopic property and see if everything ties together. So I'm going to show you that we have actually been able to do this. And of course, this was just there to just remind you, just briefly for those of you who were not there yesterday, we use STM, which allows you to do imaging of the surface under constant current situation. We can image the atoms, defects in the samples. We can do spectroscopy as a function of energy, and do spatial dependence and see if there are any anisotropies in what we measure. So what I'm going to talk about today is an experiment done on bismuth, just a single crystal of bismuth. Okay? So I think of bismuth as sort of like one of the, what I would say, the first quantum material, if you like, because you can make it very clean. You can have a sample with very high mobility. And of course, this allowed Kapitsa to basically see quantization in resistance and magnetization very early on in the 20s. And it's a system which we already know from the bulk electronic structure. You have multiple electron and hole valleys in the material. So this is the bulk electronic structure of bismuth. Basically, it has 3 electron pockets and a hole pocket. This is not going to be so relevant to our experiment because we're going to be studying the surface of bismuth. But there has already been, before we started, there was already some evidence that bismuth may do something interesting when you apply a large magnetic field and with relationship to the idea of pneumaticity. So these are experiments done by Kamran Behnia's group in Paris, where they took a basically high-quality single crystal of bismuth, and they measured the resistance basically in this sample as a function of application of a magnetic field, as a function of the angle of the magnetic field, measured magnetoresistance. Okay. And at high temperatures, basically, they found that the magnetoresistance showed an anisotropy which is consistent with the crystal structure of the underlying bismuth crystal. It shows this 6-fold symmetry here. But then as they cooled the sample down, they found that this symmetry was being broken somehow. Electrons would prefer magnetoresistance was lower or higher along some direction in the sample. So this is currently not really understood as to what is the origin of this phenomena, but it kind of, like the previous experiments I showed you where you measure magnetoresistance, it sort of feels like some sort of a pneumatic crystal because electrons like to flow one way and not the other. But then you might ask, okay, what's happening? Maybe it's the strain in the sample that has changed. And there's been a lot of work trying to sort this out. But this provided for us some motivation to actually take a look at bismuth at high magnetic field. So what we do is we take a single crystal of bismuth, and it cleaves rather nicely to produce a very flat surface along the 111 surface. So this is the bismuth 111 crystalline surface. If you look at it from the side, bismuth would have basically these bilayers, which are like stacked on top of one another in this orientation. It's kind of like, as I'll show you, it's kind of like graphene, layers upon layers. And when you take an STM image of these surfaces, you can find these bilayers, basically islands, one on top of one another. Okay? And there is a lot known about the electronic structure of graphene. So you do angle-resolved photoemission, where you basically shoot photons and emit electrons from the surface and measure the band structure of the sample, the energy versus momentum structure of the surface electrons. And this is the Fermi surface that you will obtain from angle-resolved photoemission. And what's shown here is a theoretical calculation, which shows in the dashed green is the bulk states. And these are the surface electronic states of bismuth that you can compute theoretically. So basically, it has for us already what we want. We have a system which has multiple valleys. In fact, it has both electron and hole-like valleys. But it turns out that's a complication, but we can separate the behavior of electrons and holes in these experiments. Okay? Now, before I go into the discussion of this pneumatic phase, let me just take a little digression about this surface of bismuth, which is interesting by itself. Because if you look at these bilayers from the top, they basically look like graphene. Okay? And if you remember, the original proposals for topological insulators by Meillet and Kane were basically graphene with strong spin-orbit spin-orbit coupling, which we know is not very strong in graphene, but in bismuth is actually quite strong. Uh-oh. Skip this version. That was funny. Okay. So in fact, calculations by Murakami basically showed that if you could isolate graphene in a bilayer, it would basically be your ideal topological insulator. This topological insulator would have these edge modes running around the surface of graphene. Of this 2D bilayer of bismuth. In fact, when we look at these, this sample when it's cleaved, as I showed you, we can get very nice edges, which are apparently these zigzag edges of bismuth. And I'm not going to go into the details of this too much, but we can do spectroscopy. And we can see that when we do tunneling spectroscopy on the surface or on the edge, we measure different properties. And when we are at the edge of the sample, we see a tunneling density of states which is consistent in its shape, basically a square root behavior of a one-dimensional edge state running around the edge of these graphene bilayers. And they look pretty beautiful if you tune the energy to this singularity of the 1D surface state. You can basically edge state. You can basically image these states running around the bilayer of bismuth. Okay? There are special things at the corners seems to be that you couple very strongly to the bulk of bismuth. And that's why the surface state seems to get hybridized as you get close to the corners. Okay, so let me not get into the details of these edge states, and let's go back to the bismuth surface and think about what we do in high magnetic field. Now, we can actually study the surface state of electrons on the bismuth 111 surface. Although they're very, very clean, we can dirty them up with putting a few defects, and that allows us to basically look at the scattering of quasi-particles in these surface states. And we can actually use this technique to actually confirm with our experiment that indeed we have this, the band structure that's given to us by the angle resolved photo emission can be related to these standing waves that we see in the quasi-particle interference. So this is, if you like, a way to image this 2D electron gas that's living on the surface once you add a few defects to basically scatter the 2D electron gas that's living on the surface. And this was done intentionally by depositing atoms on the surface. Now, bismuth is heavy, as we just talked about. So these band structures are basically very strongly Rashba split. Okay? And this is a measurement from, this is a cartoon of the result of spin resolve ARPIS measurements, which is basically telling us that these band structures, these hole and electron valleys, are basically the spin degeneracy has been lifted. Okay? So when you think about applying large magnetic field to the sample, you do not have to worry about the Zeeman physics in this problem because spin has been taken out of the problem. Okay? Is that clear? Ask questions. I don't bite. Okay, so what do we measure in STM? Well, I showed you we can image these surface states with this scattering, but let's now look at the density of states, which is just measuring on a clean terrace. You can do tunneling density of states as a function of energy, and you can see these features, and these features are basically related to these Van Hoff singularities of the surface states. Okay? And this is what you measure in zero magnetic field, so you can kind of understand where you are in these features relative to the band structure that we know from both angle resolved photo emission studies and from the theoretical calculations. Now we apply a very large magnetic field at very low temperatures. This is done at sample temperature of about 25 millikelvin, electron temperature of about 200 millikelvin. And you can see intense, perpendicular to the surface, you see intense Landau quantization with lots of different spacing. Okay? So to figure out what we are looking at, we can basically make these measurements as a function of magnetic field. Okay? And we can follow how these peaks basically disperse as a function of energy as a function of magnetic field.
So where did you get your 14 Tesla magnetic field?
I paid about, I don't know, $900,000 to buy this cryostat. And that's actually not a very large field these days. But 14 Tesla is easy to get in a cryostat, but people go to much higher fields. But as far as STM goes, there are not that many instruments that can go to this very large magnetic field. This was measured in the middle of the terrace. Okay? And as you go close to the edge, that actually is an interesting question. As you go close to the edge, these peaks seems to get dampened out, suggesting to us that the edges, that the step edges, are actually providing some sort of a contact, if you like, is where these electrons can escape into the sample bulk. Okay? Another thing I should mention is that by 9 Tesla, the bulk of bismuth is already in the quantum limit. Okay, you have all the electrons in the bulk in the first Landau level, and the surface hasn't gone to the quantum limit as you'll see in a second, but it's getting very close to that. So let's go back. I told you that with these markers, right, in zero magnetic field already, we kind of know where we are relative to this band structure of the bismuth 111 surface. And let me go one slide back here. So we have these we have these hole pockets, which are, there is 6 of them, 6-fold around. We have an electron one here, and then, I think I lost it. The electron pockets here outside are also 6-fold. So we know where we are relative to this band structure. And so what we can do is we can make measurements of these peaks as a function of magnetic field. And that's shown in this plot, where the intensity is basically the height of the conductance in the previous plot, where these are the peaks, okay? And you can kind of see that there are lines that are going this way, and there are lines that are going that way, and there are lines that don't change very much, and there is some sort of coloring that's coming in the projector here. But you can kind of see. So from the slope of these lines, we can basically assign whether they are electron-like orbits or hole-like orbits. Okay, it's very simple. And we can even index them, because we know basically where the top of the band is for electron and hole-like band. And we know that by 14 Tesla, at the chemical potential, we are basically such that we have occupied n equals 4 or n equals 3 of the whole states. Okay, we are in the 3rd Landau level, if you like, of the whole states. And somewhere in the 10th or 11th Landau levels for the electrons. So if we had more magnetic field, we could go to drive this system into the fractional state, but that maybe we'll discuss that at the very end. Now that was a sort of a broad view. Now let's zoom in on these levels as they're traversing basically the chemical potential, which is at 0. So you notice that as they're going along, here is very clearly, you can see that they just get hung up at the chemical potential when they are crossing 0. And it's as if basically you're bringing this level that's unoccupied, and you fill it up, and you wait till it's filled up before it crosses the chemical potential. Okay? So this kind of behavior is basically telling us that somehow we have a constant charge density on the surface of this 2D electron gas. And this is somehow perhaps set by the bulk underneath of the sample, keeping basically the charge constant as we adjust the degeneracy of these electronic states with the magnetic field. So compensation may be also playing a role. These electron and hole orbits, they seem for the most part, when they cross one another, basically what we see in the spectra, they just sort of add. But there are actually some places where there might be some avoided crossing. OK, so what did we do here when we did this assignment? What we did is we basically said each of these peaks corresponds to filling a Landau level associated with those 6 hole valleys that I drew for you in the previous slide. Okay? So you look a little closer, and you find that these peaks are actually, if you measure with a finer energy resolution, can be further split. Okay, so I'm going to mostly focus on the whole Landau levels for most of this talk, okay, which are these levels. Okay? And if they're completely symmetric, you just get one peak. But as we discussed, if something breaks the symmetry of the system, these peaks can be split, and you can occupy some subset of these whole levels relative to others, depending on what is the perturbation that's being put on the system. Okay? So what we see here is in this particular area of the sample, and this is area dependent, as I'll go into the details here, there is splitting which splits this peak into 2 peaks. One is brighter than the other. And you notice that these peaks are very bright here and less bright out here. And the reason that is that as you go away from the chemical potential, the lifetime of the quasi-particles basically is getting shorter. So that's why these peaks are very sharp when you're right near the chemical potential. Okay? So we believe that this splitting, which is affecting all the hole levels in this particular area of the sample is just due to the strain. It's nothing but some strain in the crystal. And our evidence for that is basically has to do with the fact that this type of splitting that we see of this 6-fold degenerate level is position dependent. So some places would be 4 and 2. I call this 4 and this 2 because this is like twice as bright as that. And then as you march along the sample, so this splitting corresponds to this splitting here, for example, and you go somewhere else, and you see that now you have 3 peaks. Okay? So indeed, some underlying perturbation, most likely the strain in the crystal, is just making the electrons choose the occupation of some valleys relative to the other. Okay? And which one is chosen first relative to the other, it depends on the details of the strain. Okay?
But all of them are just hole values. They're not the hybridized hole electron values?
Yeah, these are all hole valleys. The electrons also, you can see the electrons go through. Okay? I don't think they also show some features. See if you zoom in. So this is the electron state. If you zoom in, they also show some splitting. But this is also very hard to study because sometimes you can't get the electron in isolation without the hole being nearby. So there is some charge transfer between the electron and holes which could complicate the analysis. But the holes is very straightforward. Okay? Now, what we found is that if we bring one of these levels, let's say the 4-fold degenerate level, and bring it close to the chemical potential, we see an additional splitting that can happen. This is what you would be looking for if you were looking for this exchange-enhanced splitting, just as I showed in the theoretical proposal. So here you have 2 peaks. This is associated with the hole number 4 state. And they're just traversing. They hang up as they come close to the chemical potential. But then if you zoom in here and look at the spectra in detail, you see a number of peaks. This one is associated with this level going off that way. And these 3 are associated with these 3 things, basically splitting. And this is what you would be looking for, is this exchange-enhanced splitting having to do with the interaction, which only happens if you put this level right at the chemical potential. Okay? So it looked like we have 2 kinds of effects. One is due to strain, and the other one is really due to the interaction having to do with bringing this level to the chemical potential. That's why you only observe this effect at the chemical potential. So it looks like we have at least the first ingredient of what we were looking for, an electronic system which is due to the exchange. It picks some valleys over the others. And of course, the next question is, can you tell whether, which direction has the electronic system has picked? So the natural thing to do is to sit at each of these peaks and basically take an image of the underlying surface. Now, when we started to do this, we had no idea what we would see, okay? But the natural thing to do is to image it and then talk to the theorist about what we found. Yes?
Do you see a splitting of the 2 into 1 1?
Yes, we actually do, and I'm going to show that towards the end. So that becomes a more interesting case. The question was whether you see a splitting of 2 valleys into 1, and so naturally, when you have this 6-fold degeneracy, right, you would think that if you preserve inversion symmetry, you would just get always pairs of 2. And then let's return to that question towards the end. OK. Experimentally, you just pick an energy. Here is minus 230 is this guy. And we take an image of the sample. OK? Now, this sample was slightly disordered intentionally. And we found that that brings out features in the data very slightly disordered, just a few defects. And you can clearly see elongated shapes in these tunneling conductance maps. Okay? So that's basically this is this peak, that is this peak, and that's the other peak. So this really looks like those. So if you have a 6-fold degenerate symmetry broken into 2 and 2 and 2, at least let's not get into the details of what these maps really mean. We're going to do that in a second. You can clearly see that the orientational dependence of these pictures tell you that indeed you have broken the symmetry. And since this one was basically driven by exchange interaction, this picking of this direction is done basically spontaneously. Okay? So let me show you that a little bit more detail. So here is a situation at one particular magnetic field. These are against the Hall states. We know they are Hall states because they go in a certain direction. We have them identified as a 4 and a 2, okay, because that's the 2 pair we get. When we image them, we image this one. You can kind of see there are rings going this way, ellipses going this way, ellipses going the other way. You see that? And then when you image this one, there are ellipses going in the third direction. Okay? And then same exact area, same exact atomic, well, you figured that that's a defect. You just tune the magnetic field from 14 Tesla to 12.9 Tesla, which basically moves this level back up to the chemical potential, moves this one higher, and then you image the 3 different peaks. And this is basically the example of this spontaneous symmetry breaking happening. So this is kind of important because this is not being caused by the defects that we see in the sample, clearly, because here you can see that you have these rings predominantly going in one direction or another. You see some other rings, which we'll get into in a second, because now we have to really understand what these features are. Any questions? OK, good. Let me also show you that this is also position dependent. So this was one particular set of anisotropic feature in the maps. 3 peaks, anisotropic this way. Here's somewhere else in the sample, same magnetic field, 3 peaks. But what is the lower energy peak is now pointing this way rather than that way in terms of its anisotropy and its electronic structure. And these two are also switched. So this one is the same as that. These are the 2 that have switched as you went from one area of the sample to another. Okay? So clearly, we're going to also, one interesting question is the property of the domains of these phases when they come together. And that's also another thing I'll get to towards the end. OK. So I think this part is hopefully clear. Another question is, what the hell are we looking at? What are these ring-like things that show up in the tunneling density of states? They kind of look like orbits of electrons somehow. Okay, so what are they? So prior to our experiments, people have used a variety of tools to look at quantum Hall phases. Imaging, Amir's done imaging of edge modes. Other people have imaged basically different types of quantum Hall samples. And for the most part, what they have imaged are drift states. So imagine you have a sample in which you have some disorder, and you have some sort of a slow varying potential of the magnetic field, or you have edges. And these samples seem to show basically these kind of features that are basically images of the underlying disorder potential for the most part. Okay? And as the chemical potential is moving up and down in the sample, basically some states are more visible than the other. And that's, for the most part, what's been imaged. But there's one case in the literature where people actually thought about whether it was possible to actually image the Landau wave function. And this is a work done by, at Rutgers by Eva Andre on graphene. And this is a busy slide, but basically, the idea here is that if you put a defect, it could locally affect what you measure in the tunneling density of states. And But the experimental results were not very good because actually graphene is not as clean as this system is, okay? As far as I can tell in these STM experiments. So to figure out what we're looking at, let's go and make a sample that's super clean. So we have an area which is, you know, this is 250 angstrom. This is enormous as by my measure of real state on the atomic scale. And you just have 2 little atoms out of place, or maybe 3, and these are the different atomic terraces that you have. So let's zoom in. And now I think you hopefully are with me that we can tune the energy of the electron and look at the different Landau levels, like the whole state 0, whole state 1, whole state 2, 3, even though some are above or below the chemical potential. Okay, we can tune the electron energy and image at that particular energy corresponding to that peak. And now what you see is that, okay, here, okay, there is an ellipse running this way. Okay, we think we understand there is some symmetry breaking. And if you look carefully, you see that this one has only one depression. This one seems to have a depression and 1 ring. This one maybe has 2 rings, maybe more. It's not completely clear. And if you look at this one, you can kind of make out that there are multiple rings associated with this one little feature. Okay? So what do you expect to see? So let's go back to elementary wave functions of Landau levels. Okay? So these are done for a situation where you just have a symmetric band structure, if you like. Okay, just the Fermi surface as a circle. And as you all have learned on your mother's knees, these are basically what the Landau level wave functions look like if you solve them in the symmetric gauge. Okay? So you notice that as I go up in the index, I basically get more and more rings here, as you would expect. Okay, so the 0th Landau level, 1 ring, 3rd Landau level, 3 rings. So that's at least consistent with what we're looking at. But how does this work? So before I show you how it works, let me just modify this by thinking about the wave function made out of these whole states. So instead of taking a symmetric, basically, state with 1 Fermi surface, I have a situation where I take, let's say, a pair of whole valleys, okay, and I basically compute what the Landau level wave function would look like if it was made out of those whole states instead of, for example, a circular hole-like Fermi surface. And essentially, all you have to do is just elongate, sort of do a deformation of your x and y axis. And the wave functions you can basically look up in books. And essentially, by just making this transformation, which is simply gives you a ratio of the electron mass parallel or perpendicular to your orbit, you can basically figure out what the Landau wave function would be. And for this pair of whole orbits, or actually for just picking one of them, let's say, ignoring the exact shape that has a teardrop, just taking an elliptical one, this is what the wave function would look like for the 4-4 state. Okay? So this one is, so I just picked some this is a calculation. But in the experiment, we can take an image of the underlying lattice with high resolution, which I didn't show. And then, indeed, those are the crystallographic directions. Thank you.
And the vast degeneracy is gone now? With these entropy? So the normal, Landau levels are highly degenerate normally, and there's many ways of widening them.
You haven't told us what the energies are. You haven't told us what the energies are.
Right, I'm asking.
What do you mean I haven't told you what the energies are?
Go back to, yeah, so all the M, if it's circular, all the M's have the same energy and the N's have different energy.
Right. So basically, what you can do is you can. I'm sorry?
There's no binding.
There's no binding. So I guess the key question is, what does a defect do? Okay? And what a defect does, let's look at these defects. The defects tend to be a lot smaller, because the sample is super clean, than any length scale in the problem, the magnetic length, the wavelength of the electrons. And you can basically think of it as a delta function. Okay? And essentially what that does is that if you go back to these wave functions, only one of these for each Landau level gets affected by a presence of an atomic delta function defect. And it's only the one that has its maximum at the center. Right? So basically, if I add a delta function impurity, it will remove the degeneracy of this level with all these other ones, leave all the other ones alone, but it shifts this state to some other energy, up or down, I don't know, but away from the degeneracy of all these other ones. But that same defect does the same thing to all the other levels as well. Okay? So the way this experiment works is that think of a Landau level of a particular index, and think of adding a delta function potential. What it does, it takes a level from the center of the Landau level, and it shifts it either up in energy or down in energy, depending on the sign of the defect. It can be attractive or repulsive. And now think about what the STM experiment is doing. The STM experiment is basically taking a sum of the density of states at a particular energy. So if I park my STM tip at this energy, I can image all these states, and I will see that this one is missing. So if the sample was perfect, I would see, of course, nothing. But if I put a single defect, it just shifts one energy, one level up, one level down. And when I take an image of the sample at the center, I see that that one state has gone missing. And that basically becomes my way of imaging of these Landau orbits.
Can you extract the sign of U?
Well, we can. So let me tell you, the question was, can you extract the sign of U? We can if we go find where the state went to. So if it's gone missing here, we can go looking for it up in energy or down in energy, and I'll show you that we can do that. So essentially what these images are, these dark images, the one that are basically missing orbits from the center of the Landau levels. And now you can see that the story is coming together in the sense that the directionality is picked from whatever mixture of the Landau levels you use to create your state, whatever the underlying values you have picked. And the impurity allows you to image that particular Landau orbit, and the breaking of the symmetry has to do with basically what is the broken symmetry in the underlying Fermi surface because of strain or the interaction. So you can actually match these experimentally measured shapes to the theoretical one quite well. And the only adjustable parameter here in the experiment is basically the ratio of the mass anisotropy that you would use to capture the shape of this elliptical orbit. And that's something that's in agreement with angle resolved photon emission measurement, which can extract this mass as a function of direction. Now, you can do this in more detail. You can measure the size of different orbits, for example, different hole orbits or different electron orbits as a function of magnetic field. And essentially, of course, if you fixed n and you just look at the size of the orbit, it would just go like as the size of 1 over square root of b. And you can check that for the hole orbits. For the electron orbits, it's kind of hard for us to basically measure the same level. So this is n, 8, 10, and 12, because these are dispersing so rapidly that we can't catch them in the experiment nicely. But if you vary both n and b, you can also capture the shape of the electron orbits. And now coming to your question as to whether you can extract what the strength of the interaction was from the impurity, you can kind of see in this movie. So here's one of these peaks. And you can image all the way over here at 0. And then instead of seeing a dark spot, you see a bright spot. Okay? So what has happened is that there was a state that here at the center of this Landau level that got shifted to this 0. And this is why it appears as a bright spot here rather than as a dark spot. But now if you basically do this imaging as a function of energy, you can see that the dark spot turned into a black spot. So basically you can capture, OK, this is an electron orbit that got shifted from this particular energy to this other energy. So you can actually make a measurement of the sign of each of these defects. And this is just the details of that. You can actually convince yourself that you have this contrast reversal as you go basically around a sweet spot of the energy. And you can convince yourself that these are actually associated with a particular shift, which is like a few hundred micro eV for each of these defects. These are very, very, very weak defects for the electrons moving on the surface. How am I doing on time? 5 minutes, 10 minutes? OK. So now, going back to our project, we have everything. We have the wave function. And we know they are basically Coulomb interaction. So you can compute basically everything about this problem. You can actually take the original wave function with the anisotropy that we know from the band structure and basically compute what the size of the exchange interaction should be when the electrons will split. The only adjustable parameter you need in this theory is the dielectric constant that you would use in the calculation. And we picked the number that's about half of that of bismuth. And then for each of these whole orbits, you can essentially estimate, calculate just what the splitting should be from this simple Coulomb integral. And you can then use this fitting parameter for this epsilon to predict other ones. And this seems to work very well with the experiment. So there's very good agreement between what we are seeing for these numbers for the gap and the size of the gaps that we measure in the spectroscopy. So let me close by showing you some of the most recent results. And this is mostly work in progress in this experiment. So clearly we have these pneumatic phases. And now the question is, what happens at the domains between these pneumatic phases? Okay? And so we've done a lot of experiments to look at different areas of the sample. We got first started just looking at different areas which there were a lot of strain in the sample that you could even image because of some structural defect in the sample. And this is just basically showing you, the problem could be messy if there are basically structural defects. But very recently, it seems like we have managed to become very good at finding these domains. But domains in areas of the sample that are super clean. Okay, so look at this. This is 500 angstrom. This is not dirt on the projector. This is actually a single defect that you see in the sample. Okay, so the variation on this surface is 40 picometers. So it's like almost a perfect crystal. Okay, and then now you put it into this, the right conditions for this pneumatic phase. And then this is the conductance map of this exactly the same area. Okay. So this is a domain wall, as you can see, between two different regions of the sample, where on this side, you have rings going that way, you have rings going the other way. And sometimes I see rings also going the other way, but remember the shifting of the impurity potential up and down. So you have to, if you keep everything straight, figuring out what level has shifted from what original Landau level up or down, you can convince yourself that basically you're looking at a region of the sample here where the symmetry is being broken one way and the symmetry is being broken a different way.
And then the defect has a consequence in the middle because there's a black streak in the center of the nested ellipses of the multiple.
Yeah, so for example, this defect is causing this little ellipse here, which is for this particular Landau level. But of course, it's too small for it to give rise to such a signal here, which is just spontaneously forming between these two electronic phases.
The other black spots are other defects that we just don't see on the
Exactly. They could be subsurface defects that are very difficult to image in this topography, but they are basically trapping, just like we discussed. And now you can go across these domain walls and try to understand what's going on there. So now hopefully you're used to these plots. These are basically peaks that will corresponds to degeneracy of the Landau levels being lifted. Okay? So if I image here, I would get one kind of ring, and if I image here, I would get a different kind of ring. And now what you see is this nice level crossing that's happening as you go across these domain walls. Okay? So we are interested to try to understand what is the nature of the edge states between these pneumatic phases. There seems to be some disagreement among the theorists whether these should have sort of edge modes or whether they should be gapped and, or not. So these are some of the questions we're trying to figure out. And somebody asked about splitting between a doubly degenerate. So this is six-fold. We talked about how you get two-fold, two-fold, and two-fold. What about two-fold? Can you ever see it split? And recently we are actually seeing that when we sweep some of these doubly degenerate level in a very clean area of the sample, we also see splitting them into 2, 1, 1 peak. Now, this is a particularly interesting situation because the question is, what have we done? Have we broken the inversion symmetry in the sample? Is it occupying this level versus that one? Or is it going into a symmetric or anti-symmetric combination of these whole states? Okay, so this is one of the questions that we are trying to address. So for example, theoretically, what you would expect is that if you create, so if you have basically these two valleys, and if you make symmetric or anti-symmetric combination, of course you would, when you sum the wave functions, you would get these standing waves having to do with the momentum difference between those two valleys. And experimentally, you would expect to see not the features I've shown you, but if you zoom in and look carefully, there should be modulations basically corresponding to the superposition of those two valleys with one another. So we see something like it, but the details aren't working out very well. So let me show you another example of a defect and where we zoom in with very high resolution. So this is an area, and then you have this 1-1 splitting, okay? And you can kind of make out what I was showing you before, this ring-like feature. But now they have zoomed in, and you can kind of see what the theory would expect you to see, which is these standing waves having to do with the superposition of the two valleys. But then when we go to the other energies, we seem to see things that don't seem to match the theory at all. Okay.
Where's the lattice constant on this scale?
Ooh, it's tiny. So sorry, this is so new that I don't even know whether they have the scale. Let's see. So this is the magnetic length. This is probably 80 nanometers, 70, 80 nanometers. So let's see. Yes, lattice constant is just irrelevant. It's super tiny. But these modulations, okay, I think I have a number here. The modulations we see here is 12.5 angstroms. So this is 12.5 angstroms between each of those ripples that you see in the background.
The lattice constant is 5 times smaller.
The lattice constant is at least 5 times smaller. I don't remember the exact number. So right, there is some very interesting structure in terms of these Landau orbits or what's happening near these Landau orbits and a defect, which we don't fully understand. So this is one of the things we're working on. And so there is a lot of finer details in these experiments that are just coming out when we look at very fine length scales, which has to do with these issues of what are you doing? Are you making a superposition of states or whatnot? So also, the question of these domain walls is also an interesting question, whether you can have, if you somehow picked, let's say, one valley versus other, whether you can have some sort of ferroelectric almost like behavior at the domain wall between, whether these are ferroelectric type quantum Hall phases, and at the boundary here, you have some interesting charges basically accumulating in the sample. So these are all issues which we are trying to sort through. OK, so let me conclude. So bismuth, people have worked on bismuth forever. And so it continues to surprise us. It has this very nice 2D electron system. And we seem to have done something that, I hope I thought about a long time ago, but I never thought it was possible to actually see these Landau orbits in the experiment. And of course, this makes us think about what will happen if we drive this system into the fractional quantum Hall state. And what kind of pictures can you get there? Whether you can use defects in very much the same way as we have used them here to image the wave functions of the underlying state by just shifting them up and down in energy and to removing them from the background. And I think that there is, at least from the perspective of pneumatics, this is a case where you can clearly say that interactions is basically driving everything, because we can tie the interactions directly with the symmetry breaking. And so there is no question that the strain is there, but it's not the driving force. And this is the first case that we have come across that we can clearly make that clear, because we also have the underlying wave functions where we can calculate pretty much everything about the system. So with that, I stop and take your questions. He's clearly lazy.
You mentioned this, but if you dip a magnetic field into the plane, can you enhance these, can you modify these settings? Is that a way to
Shifting. So the question is, what will happen if you apply in-plane magnetic field? So in the quantum, in these previous transporter studies of 2D electron gas, parallel magnetic field does a lot of things. We haven't tried it yet. That's a good question. Why would you expect a parallel magnetic field in this particular? So there you at least have the Zeeman term to play around with. Here you do not. So we could discuss it later.
be some spatial extension of the surface state?
I see.
You're breaking the symmetry by hand.
Breaking the symmetry by hand. That was the key remark. Question?
Any other questions? So I was wondering, why are the electronic Landau levels much narrower than the Hall-like ones?
Narrower in which sense?
Well, just in the beginning, when you were showing these Landau fans, the electronic.
I think the one
states-
shown here, for example.
Oh yeah, for example.
Oh,
They're
that's
very, very sharp.
I'm not sure. Yeah, I'm not sure why. I think part of the reason, well, perhaps part of the reason is when you plot the data like this, you do not really actually, what you have to keep in mind is the electrons are dispersing very rapidly. So they might look sharper than they really are. I have to go back and look at the actual cuts. They might not be as much
The
sharper.
individual pixels, yeah.
I see. They look like pixels here.
Actually, when you show the picture, there are actually two kinds of electron states. There's the anisotropic
This is the one at the center of the zone. We never see the one outside. I don't know why. The one at the very edge. I don't know why we never see that.
Inti.
The case in which you see this extra wiggle, the thermal relation, these things from 2 to 1, 1. Have you ever seen, say, the experience from 2 to 1, 1, in which you don't see?
We don't have enough data on that. I would say this particular feature, I don't think we have all the data in there. I'm not completely sure. There are very few data sets like this right now, but we can check for that. But if you go to some of these other peaks, I think it's shown here, we also see some additional features which when we zoom in with very high resolution, which we are not completely sure what they are. Okay. So there seems to be, this is clearly an interference effect. So this one at least matches the theory. These features, we see a lot of different things like this one, where we are not quite completely sure what is causing the interference that's giving rise to these things that you see in the data.
So
This
did
one-
you Fourier transform them just to see what they give you in
Yeah,
quantum space?
right. So that's what we're working on, trying to see whether this is somehow related to. So it could be that the impurity is mixing electrons from different values. And actually, the effect here is not really a feature of the underlying state, but rather what the impurity is doing to your measurement. The impurity could be mixing different values rather than the values being themselves mixed to begin with. So that's another thing that one has to keep in mind as well.
That's not in the domain wall. This is at a.
Yeah, there are no domain wiles nearby. None. This is just very clear, very clean sample.
All right. I think we'll thank Ali again.
Thank you.